Yeah, question 14, 15, 16, 17, and 19 we have up next, right? What number corresponds to the activation energy of this reaction, right? Our activation energy is the hill we have to get up and over for the reaction, right? So my activation energy would be number 2. The energy of my transition state, which many of you are choosing for some reason, right? The energy of the transition state, that is number 3. A lot of people are going with number 3. That is not my activation energy. The activation energy is the energy, right, from my reactants. Here's my reactants. I have to put the energy in to get this reaction to go. So that is the energy right there, just number 2. Question 15 is on 2 pages, it looks like. What number corresponds to the energy of the transition state? Oh, okay. Well, I answered that question at the same time because, yeah, the energy of the transition state, my transition state is right here, and that's my energy, right? You're at the peak of that mountain, and you could go either way. We could go back to reactants or forward to products. We definitely went over reaction coordinate diagram. The other things that we talked about that you should know, like the images of, would be the graphs for a first order and second order reaction, like what's on the X and Y axis for those. All right, question 16. You're going to kick yourself when you see how easy this question is. All right, a compound decomposes by a first order process. If 12.5% of the compound remains after 60 minutes, the half-life of the compound is what? Well, for half-life, right, we start with 100% of the material. After one half-life, we have 50%. After another half-life, we have 25%. And after one more half-life, we have 12.5%. So we go through 1, 2, 3 half-lives, all in 60 minutes. So each half-life would be 20 minutes because of that. We can do that in this case because this is a nice, even half-life. If the question said, how much is left at 5% or how much is left at 17%, right? Then we could not do this. We'd actually have to do a calculation. So it would be a harder question, but if it was not a nice half-life number, what we would have to do is we'd have to do the calculation for a first order rate law. And we would say natural log a concentration at time t equals negative kt plus natural log a concentration at time 0. And what we would do is we basically would convert our percentages to decimal, and we would say, okay, natural log of my concentration in the future, so 0.125 is my concentration in the future, equals, I need to find my rate constant. I need to find my rate constant to find half-life. So this point in the future is 60 minutes. And you might say, I don't know an initial concentration. They don't tell us an initial concentration, right? It's 100% would be our initial concentration. 100% as a decimal would be 1. So then natural log of 1 is 0. That falls out of the equation. We can solve for k, our rate constant. And then once we find k, our rate constant, we know t 1/2, our half-life, equals 0.693 over k. So it would be a little bit longer, but you could solve this problem both ways. If it wasn't a nice half-life, you would have to use the second way to solve the problem. You have to find the rate constant and then use the half-life equation with that rate constant to find what is the half-life for this reaction.
Would a question like that show up on the exam where it's like difficult to find?
I mean, it could. tell you the probability is not 0. I haven't even written the exam yet, unfortunately. It's going to be a long day tomorrow. Keep doing that. Right. So question 17, what is the reaction? What is true for a reaction at equilibrium? At equilibrium, what is true, right? The amounts of reactants and products. I got to read the question again. What is true for a reaction at equilibrium? I don't think my question makes sense unless I'm missing something. What is true for a reaction at equilibrium? I should probably say like what is equal, right? The amounts of reactants and products. Maybe these sentences just aren't complete. The amounts of reactants and products are equal. That is not true. Right, that is not true. Concentration of reactants and products are not equal. The forward and reverse reaction enthalpies, the delta H, we didn't talk about that. That's not true. And then the rate of the forward and reverse reaction are equal. I'm going to say that was poor wording on my part. I should have done a better job proofreading that question. But yeah, at equilibrium, right, the rate of the forward and reverse reaction is equal. And nothing else. Concentrations could be totally different. Mass, moles could be totally different. Delta H's could be totally different. It's the rate that is the same. Question 19, it looks like for the following reaction, following reaction, nitrogen, hydrogen to ammonia, KEQ equals that. We set up a new reaction, have 1.25 molar nitrogen, 2.5 molar hydrogen, and 0.5 molar ammonia. What direction will the reaction move? So we are calculating Q. All right, so Q is calculated the same way we calculate K, except for K, KC, KEQ is equilibrium only. Q can be used at any point in a reaction, but can be used to tell us what direction that reaction is going to move. So Q is still written the same way. It's still going to be products over reactants. So I've got ammonia squared over nitrogen, hydrogen cubed. I plug in Q. My ammonia concentration is 0.5 squared. My nitrogen concentration is 1.2. My hydrogen concentration is 2.5 cubed. So square that and then divide. Divide that by, let's see, 2.5 cubed times 1.25. And I get a Q of 0.0128. So what does that tell us, right? If we take a look, KEQ is 0.00123 and Q is 0.0128, right? That tells us that Q is greater than equilibrium. What that means is we went beyond equilibrium. We want to get to equilibrium, right? Equilibrium is where the reaction wants to be. We went beyond that. So the reaction is going to move to the left to get us back to equilibrium, right? We remember in class, we turned that into an arrow to say, okay, the reaction wants to move to the left to get us back to equilibrium. If we move to the left, we make more reactants, right? Our reactions are typically run reactants going to products. So moving this to the left, we're going to form more reactants to get to equilibrium. All right, I'll pause the video here and then we'll start back up with the next group of questions, 21, 22, 23, 24, 25, and 27.